Hi guys, so we have the laser light source here, and we use this to adjust the power input to preventing saturate, and we use the different apertures to finding the different diffraction patterns. As we positioning the aperture and this camera, we can center adjusting the position of the image computer.
What is up, guys? We are going to take a look at why the double slit and single slit are different. In a single slit, our profile looks like this, just like a nice little diffraction pattern. Now with the double slit, we get a modulation that looks like this. It has little modulating frequencies with the overlaying envelope. And why is that? That's because the interference that's caused by the two slits results in the smaller order diffraction pattern, while the actual interference pattern that results just from the overarching slit width results in the big one. In our experiment, we also had a circular, square, and we had a triangular aperture. The circular resulted in a somb-like function, and then the square aperture results in a sink-like function. The triangle is a kind of a mixture.
On the top row, we have the circular aperture followed by the square and the single slit, then the triangular on the bottom followed by the double slit. Lastly, you can see our experimental and theoretical graphs.
Alright guys, so for part B, this is our setup. We have a laser of 632.8 nanometers coming into this detector, which measures the waist in both X and Y coordinates. So we move this, starting very close to the laser at a distance of about 0, moved it all the way back to the end of this rail. And the result is we were able to calculate how the waist depends on distance. And we did that for both X and Y and compared it to our theoretical. Alright, so for our calculations, we have the theoretical waist here times the initial waist and the rest of the equation there. So by plugging into that, we were to get a theoretical graph that matches very closely to our experimental data. And we see that the graph in the waist of the X and Y are also very similar, meaning that we have basically a circular beam diameter versus an elliptical one. In addition, we can calculate numerical aperture, and we found this equation by using some trigonometric identities. And the result is that we have a numerical aperture of about 0.0005, which is very small, meaning that we don't have much divergence in the beam, and the result is that we have a very straight beam. Lastly, we were able to calculate the divergence angle by taking the inverse sine of the numerical aperture, and the result is 0.02 degrees.